Okay, so basically, whenever we're talking about measuring the permeability at the field, then we have to do something where we can look at the time lag between several points. That's how it's going to work. So the first one is known as the pumping test. So the pumping test is basically having a borehole
and pumping the water
and then pulling the water out. So if you pump the water out, then it's going to create a drawdown curve. And if you know that the distance between like the characteristics of the drawdown curve, then you will be able to find out the permeability of it. So the question is, how do we know, like looking at the drawdown curve, how do we define the characteristics of the permeability? Any idea?
we need to place two monitoring well.
Okay, so we place the monitoring well, but first of all, what is the basis for developing a test method based on the pumping test?
Curve or something like that.
What is the overall idea? Like, what is your feelings?
Like shape of the drawdown curve.
Okay, so how the shape of the drawdown curve will be affected with the permeability of the soil?
The more permeable the soil is, the more curvy zone we will see, or drawdown curve we will see. What should I say? The slope of the drawdown curve will be very steep.
Will be steep.
Will be very steep.
Okay, if you pull it, right?
If the soil is really permeable.
Well, when you pull it, but think about it. This when you do the pumping test, you just don't take the immediate results, right? You run it for some time. So when it reaches to calibrated condition, then you start doing it, right? So let's say you pull it at the beginning, you see a very sharp drawdown curve, but later on what happens?
It becomes parallel again. It near to parallel.
Yeah, it will have a like a adjustment, balanced condition, right? So there will be like some water will try to travel from the side, and it will try to generate something. So when it's trying to develop heat, something like that, what is the major difference will be between sand and clay? There will be one difference for sure. What will be that difference?
Sand will have like a constant Q. After some time, like after you do the drawdown, it will just be constant over time. Like it's whatever value of Q, but the clay soils will just keep decreasing the value of water we pump from the well.
Okay, so for clay soil, we will see that it will have a decreasing. Will it be a decreasing value amount? Even though it depends.
It should be. Yeah, it should have some decrease in the value. Or not the value of the Q, but whenever you do like when you do the water level test while you are pumping, you should see the water is just going down, the head is going down. While in sand, at some point you will just keep having a constant hit.
Okay, that's one thing. Very good. And then there is another difference. The extent, the extent area. For
Influence area
will be very narrow.
Radius of influence will be very
Low for clay or sand.
for sand.
For sand or clay.
For clay.
For clay, influence area is going to be high or low for clay.
Lower.
Lower, higher.
More surface area means more permeable.
No,
Because the water will just take some time to come from.
that's the permissibility, yeah, over is that, it will be lower. Right? Think about a pressure valve, so you're trying to cool the water. In the sand, all the water from outside will try to travel and try to feed in, right? So it will fill in whatever that the water is being pulled out from that location in the sand, because water can travel very easily, no resistance. For clay, there are water, but you are pulling the water out. The water outside cannot just get in and fill the void, right? So in the clay, it will be more localized. And what's gonna happen between the silt or in between, like changing the permeability. So it's not going to have like, it will have some influence area, but there is a time lag. So for clay, you'll see no time lag. It's like it just dry. You pull some water out and then it stopped. You don't need to do any test. You do it for some time and you'll find out, oh wow, what happened to the water? Maybe we did something wrong. It's not. It's basically there is no water available there. It will take time to water come in and develop something, right? Basically, pumping test is not very useful for clay soil at all. You know, but if you want to find out like the permeability in a high permeability soil, in that case, permeability the pumping test is very useful. Okay,
For clay, it is slug test, right?
which one?
For clay, we are more focused on instantaneous change.
Yeah, it's just like for clay you can use it, but your time span has to be very short. You won't get a continuous data in clay. You'll get data for some time. You can use it, but you can get it for some time. For clay now, there are other way of getting very good results. One is by doing the CPT. CPT is a terrific test for clay. It works really great. If you have a piece of bone, then you can push it and then you look at the time difference. That gives a very good results using the CPT. You know, can you use resistivity to find out the permeability?
Yes, by some
I think so.
back calculation.
I think so.
Because
Because you can see from the result resistivity the void.
yes,
You can measure the void that later we can create.
yeah, we can measure the void, but even if we can measure the void, resistivity is not instantaneous there. So it's difficult for using the resistivity, or it's difficult by using the resistivity to come up with like what is the condition, you know. Okay.
But can we understand the permeability of some soil, not from direct result, but passive result from resistivity test? I mean, can we have some idea about permeability of some soil using resistivity test?
Yeah, sure, we can. We can. Like, but it is not gonna be very accurate. But we definitely can. Because first of all, using the resistivity, we won't get the direct results, but we will get the indirect results. Indirect results for sure. No question on that. Because looking at the resistivity value, we know what is the type of the soil. If you know what is the type of the soil, then we can also find out like the characteristics of the soil. You know, does it has like what is the characteristics of the sand, silt, or clay? And knowing that there are like some other ways of calculating the resistivity. For example, you know, like what is the gradation curve? You know the gradation curve, you can find out the permeability. there are some indirect ways of calculating the permeability from there. That's one way. Now, the other ways of doing it is, let's say you have a rainfall, and after the rainfall, you're looking at the resistivity result. So, do the first resistivity test, and then after a certain time, you do another resistivity test. Now, the only change in between these two tests is your moisture content, right? So now if you set a target, a certain target, with a certain distance, so you can predict like whatever the travel is going to make. You know, it can be very useful. Is like if you know that there is a rainfall and you go to the site next day, and then let's say next 3-4 days there is no resistivity, there is no rainfall at all. So whatever the moisture is infiltrated is basically traveling. If you are out of the active zone, and then if you do the resistivity, like if you ignore the first top 10 feet, and then in the lower depth, if you look at those data, then yeah, you definitely can start looking at those numbers using the resistivity to find out like what is the permeability and what is the other results. It should work. Okay. So basically, if you know all these details, then all you have to do is you need to know few numbers, you know. So basically there are like two conditions here. One is the artesian aquifer, and the second one is the unconfined aquifer. So any idea what is the unconfined aquifer versus the artesian aquifer?
Artesian aquifer, the water layer is bounded by two impermeable layers, up and down.
So it's under pressure, right? It's a pressured water.
Pressure.
So if you have a borehole or something, then you should
Flush out.
water should come out, right? Any idea of like the artesian aquifer? Anyone been to Little Rock, or there are like some aquifers where you can see like water always comes out from the ground. I think Little Rock has it in the Arkansas.
Hot spring,
Or hot spring
area.
area, right?
Yeah, it's in hot spring, there's the water was coming up.
So, but that's a hot water.
Yes.
What is the mechanism of hot water coming naturally?
At the core of the heart. Well,
Pressure difference.
I think there's some chemical process. Hello, water is flowing through some layers, and within those layers there is like some chemical process which is having a thermophilic, right? Or thermophobic.
That induce a bursting effect.
Thermophilic reaction. So if you have a thermophilic reaction or something, it should generate something. Or it pass through the limestone. It should also increase the temperature. Have you seen like you add the lime in the
It
water?
becomes really hot.
It becomes really hot, right? So that's the thermophilic process. So basically say something like that. Anyway, so if we have a artesian aquifer, then what's going to happen is like you're pulling the water, and you know that the thickness of the aquifer, K is your permeability, Q is the discharge, and T is the transmissibility, which is K multiplied by M.
M is the layer
M
of
is the
the water.
thickness, layer thickness. And so then you know that the piezometric pressure at the
It is zone.
sorry, this is HE. HE is at the surface, and HW is right here. So at the point, at the aquifer, like at the borehole. So you have the HW and HE, then you have the RE and RW. So there are two things. RE is where you have the HE, right? From the center point, RE is where you have the HE. So at the point wherever you are measuring the HE, at that point you are measuring the RE. And the second part, one is the RW. RW is basically the diameter of the well, while you are measuring your RHW. So you know all these numbers, you plug in those numbers, and you're good to go. You know, that's one way. If you have a pressure like artesian aquifer, if you have the unconfined aquifer, then all is happening is like your just equation is different, but all the procedure is same. You pull it, you have you calculate the K, you have the Q, you have the RER, WHE, HW, right? So you just plug in the numbers in that equation, and you should be able to find it out. Okay. And we have the log E. What is the log E?
11.
11. So basically, if you rearrange that equation, you should be able to find out like what is the K. And for an aquifer, unconfined aquifer, that's your equation. You know, so these are the two equations that you need. There might be a homework problem on this. That is very straightforward. There might be a similar problem for your midterm on this. Very, very straightforward. There is a problem on the pumping test. The problem on the pumping test is given. So it's like, I'm trying to find the answer. No, it's not there. So there is a problem on the pumping test. So if you see, it's like, can I say it? Okay, so basically there are like 3 oil in it. And so the first one is the oil 1, you know, this is the oil 1, this is the well 2, and this is the well 3. And it has the R is given, R equal to 400, 200, and 100 feet. You know, so the first one is the pulling. So these are the, sorry. So you have the observation well. So it's not like you have only 2, you know. So basically what is happening is you're pulling the water. So this is your well, this is your pump test, this is the pump. You're pulling the water out. So when you're pulling the water out, you will have it around curve like this, right? So now you have a 1 well here, observation well, second observation well is here, third observation well is here, like this. Okay. So in this observation well, at the time, it started increasing. Is this like as the time is increasing? You know, this is the S. S is in feet. So what is S?
Drawdown depth.
S is the drawdown depth. So from the top, right? So what is the depth here, right? This is the depth, and S is the drawdown depth. So whatever the depth water level is dropping. The different time the water level is dropping, so you can check. So if you wanna do the calculation, all you have to do is you have to do the calculation at a certain time. You know. So it's keep dropping, but they just monitor it for a certain period of time. You know. So basically, you need to look at like when it becomes a stable phase, it's like all the lines are parallel and stable, right? So you can pick any point, any line. So in this case, what is given is you have the Q and you have the M. So it's an artesian aquifer, right? So you have a thickness M, and then at T, this is given at time T, 960 minutes. You have the observation oil S1, S2, S3. You calculated it for R1, R2, and R3. Now you have the M, right? So once you have the M and you have the S1, S2, S3, so you need to find out the H, which is the HW and HE, right? We are looking at the in the equation that number is H, height. So basically what we have to do is we need to calculate the H. So these are the H that we calculate. And so we have like H1, H2, and H3. So these are the numbers that we got. Once we have it, it's pretty simple. All you have to do is you just need to plug in the number. Very simple, you know. So the only trick in this equation is all you have to do is you just need to select the S. You have to calculate the S, right? And this S you can calculate at any time. At any time, like a certain time stamp. So let's say you can also look at 800 at t equal to 800. You can look at like what are your S1, S2, and S3. But you also need to know the Q. So if or if your problem becomes tricky, the only trick it can be is Q is given at certain time, you know. So basically, for example, this is your discharge drawdown clock at 9:60 minutes. That's the only trick in this problem. Nothing else.
So the whole test is for a constant discharge, right?
Yes,
This graph is for a constant discharge. If I use another discharge, then there will be different graph.
yes, absolutely. But also remember this: your t equal to 960 minutes. That's the only trick. If so the Q you're using for 960 minutes, so you need to use the time for 960. If your Q is given at a different time, you know, then you can pick any other time.
I want to be clear about
Your T, the volume Q is given. Q can vary, right? So if your Q is given, let's say your Q is given here out of instead of the 960 minutes, let's say you have 850 minutes. In that case, from this curve, this is the curve is talking about the S, right?
Yes.
So this S you calculate for a certain time. So this is 960 minutes right here. This is your 960 minutes, right? If your Q is given for like 800 minutes or 850 minutes, so then you go there and find out what is the 860 or 850 minutes. You find out that is value, and then you do all other calculations. That's it. It's very straightforward problem. Now is, you know. And the second one is the so one is the pulling method, which is the pumping, right? Pumping method is a constant pull. So we have two permeabilities in the lab.
constant head and variable permeability test.
Constant head and falling head,
Falling.
right? So which one is better for what? Constant head is better for which material?
Constant head is better for clay.
And
Variable head is better for sand.
okay, good. Wow.
So in sand, permeability is very high.
Any other thought?
It can be calibrated easily.
Any other thought? Which one is good for what?
Which one is good for what?
Yes, which test? Like your constant head and falling head.
Well, the constant head for sand and the falling head for clays or fine materials.
Falling head. Say it again.
Falling head for fine materials like clays,
Falling head for fine materials and constant head for
sand, and
or sand. So you're saying the opposite of what Sai said. What is your thought process? Which one is good for what? And why? What are the most difficult questions in the world?
Why?
The most difficult questions are the WH questions. All the WH questions are difficult questions.
So in the sand, I think it's more variable. So you'll be using the constant pressure.
Constant heat. Okay, heat and pressure is the same thing. Okay.
In that case, as it, otherwise, for the clay, and it will be less permeable, so we'll be increasing the pressure.
No, there is no increase in pressure. You're not getting the point. Omar, can you explain why? With your arguments?
I actually said that based on the name. No,
Okay, that's fine. Do you have any argument?
I think it's because of the influence area. Sand has smaller, clay has smaller influence area. So for a small, there should be, the head difference would be somewhat sequented, I think. I don't know, actually.
Actually, I told it from my intuition.
That's a gut feeling, right? Intuition is very important. So, what is the basis of your intuition? Okay, think about it. So let's say you have the sand and clay, all right? So sand, highly permeable, right? You try to create a constant head.
It will not be constant.
It will be, the constant will be possible for sand.
Why?
Uh, because if you want to maintain the head
Yes.
constant for all time, we need a highly permeable soil.
Okay, very good. You're right. Exactly. You can keep a constant head only in sand because sand allows the flow. Sand is like pipe, right? You're not keep a pipe flow. So it's like it will create a volume and then it will drip some water out and enter the water in, right? So what constant head means what? Your inflow is equal to outflow, right?
Yes.
So your inflow and outflow can be made only possible in sand. Whatever is getting in, the same water is going out through the sample, right? Can you make it in clay? Whatever is getting in, that the same one is going out. Why?
Output will be lesser.
Because it's going to take very long time for the water to flow through the clay. So there will be like a head building up, right? So let's say you have a sample. Let's say you have a sample. Okay. So you put some sample inside, and then you add some water on it. Okay. So let's say you add some water on it. Then what's going to happen? If it's a sand, if it's a sand,
It will take very long time to,
if it's a sand, and you have water on top of it, what's going to happen?
it's very, within a very short time, the water will be,
We will flow through.
and the test cannot be conducted.
So it's going to be very difficult for us to get any data, right? So what we should do, we need to keep adding some water,
Yes.
right? So it will keep a constant head there. So whatever the flow is going out, we have to add the same water amount of water from the top, so we can have a measurement in the sand, right? And now if we do the same thing in the clay, then what's going to happen?
It's going to overflow.
It's going to have overflow, right? So for the clay, what we have to do?
Following up this.
For the clay, first of all, we need to take off the water coming from the top, right? The base idea is take the clay sample, add some water on top, and then come back after 1 hour and see if any water level drop. come back after 1 day. If the water level dropped, come back after a week if the water level dropped. Because it's gonna take the time, right? So the most critical part is the time, right? Your water level will drop down, it's gonna take time. You get my point? So basically what's gonna happen is you will see that the water level difference between the time T1 and time T2. So whatever the time difference you have, and in between you'll see like how much water level it has changed, right? That's it. And based on that, you can calculate the permeability in the clay, not in the sand. In the sand, you have to keep a constant height, no matter what. Clear? That's why we need the falling head and the constant head. So the pumping test, if you go back, now the pumping test is suitable for what? Sand. Why? It's the same thing.
Easy to.
We are cooling the water and this is maintaining our constant water, right? So that's good for sand. If it's a clay and we are trying to pull out the water, we pull the water out, the influence area, all the water is drained out, and then it's now no water is coming out from the pump. That's all gonna happen. So if we wanna measure the permeability in the clay, then what we should do? We should do a falling head test. So how we can do a falling head test? So this is the falling head test. All we have to do, we have to create a bottle, fill it with water, and then have the observation well, and then come back and measure the flow of water through that well.
Why the drawdown curve is
The opposite,
opposite?
because you're injecting water, you're not pulling water.
Oh, yeah, yeah.
Okay.
There is a concept called minus degree for Richards that what is the same principle?
You just inject the water, so you have the water, let it flow through it, so it will create the well, the opposite way. You know, and then you come back and look at the time difference. Clear?
Recharging.
This is the recharging oil.
Add the water in it, and then see. It's like how it's behaving.
In northern part of Bangladesh, the groundwater is actually depleting. So they are using the same technique,
Add the water.
adding water. For a small zone, it works really well.
Yeah, if you're gonna do it like Bangladesh is mostly silty soil. So within the silt, the most interesting thing is geotech, the permeability has a significant influence on everything, and no one cares about it. You know, but that changes everything. If you just consider the impact of the permeability in your design, you know, it really creates that's the most that's the sweet spot to be a good designer and being a great designer. If you're gonna be a great designer, then always keep in mind like how the permeability is playing there.
How permeability is going to help a designer? Yeah, actually, one of the steps.
You have to look at the mechanistic thing. So this is like looking at the elephant. If you wanna build something, then you have to have the top-down view, bird's eye view of a problem. But if you have like side view, so you just look at the elephant from one side. So you're looking at the problem from one perspective only. You have a change in the perspective, and it's going to fail. It's just a matter of time.
What design parameters are normally affected by
Everything.
everything?
Everything is everything.
There is the bearing capacity, so that affects everything.
Yes.
It changes everything. Geotech is all about water.
I was just asking the cable,
Yes.
how is going to, how to incorporate this cable in my
Okay.
calculation? That's
First of all, geotech is all about water. Now, any medium becomes permeable or impermeable, depends on its moisture content, right? Now, if your permeability is high, water flow through it very quickly. Your permeability is low, it will hold the water, right? That's how your permeability plays the game.
okay. Bearing capacity is low. If my soil has low K.
For example, let's say, let me give you the example here. In Mississippi, you have expansive soil, have the cracks on top, water builds up, but after a certain time, the permeability stops, right? It behaves like a barrier. And then it's a highly plastic soil. Now, all the water is coming in, and the water is becoming softer. You know, so you can take a very highly compacted clay and soak it into the water, and then take out. What's going to happen? Any idea? Highly compacted clay. Take it out and put it in the water. A bucket of water. Let's say you have the clay, highly compacted clay. Take it out from your standard proctor test device. You know, it's highly compacted. Now put it in the water.
For how long?
A day, 2 days, a week. Then what's gonna happen? How much strength you can expect? Does the clay will retain the same strength as it was compacted? Why?
It absorbs the water.
And
It will, like, the shear strength will be lessened.
how listen? Can you do this test for your own sake, for your own understanding? Ideally,
Money.
it will be super muddy and soft, you know, like a pudding, you know, super soft, no strength. So all the slope failures, all the foundation failures in this area happens like that, even on the pavement. You know, all it does is what? Is the water gets in, and then water is sitting there for a long time. So whatever the area water is sitting there for a long time, it becomes super soft. You get my point? That area becomes super soft. Nothing can change it. Because that's the phenomenon of clay. Clay is extremely good material when it is dry, and extremely bad material when it becomes wet. You know?
This is the reason all our roads are bumpy.
The roads are bumpy for a different reason. Roads are bumpy because you have a moisture intrusion, and then some part get expanded. But what also happens there is like why the wavy pattern. Now the wavy pattern is really distinct in the expansive side. The wavy pattern, right? So your shock absorber only lasts like 100,000 miles in Mississippi, and after that you need to change your shocks. That's $5,000 any car.
A very bad place for car.
Really bad place for car. It really doesn't matter. You drive here, your shock is gone. Same as in Dhaka. You buy a new car, you drive 3 months, then new car becomes an old car. It really doesn't matter. That's why people over there doesn't buy the new car. People always buy the recondition. Right?
From Japan.
Yes, recondition car because the condition of the road are not good. You know. And you feel it. You go to Texas, even immediately, you don't need to look at anywhere else. You just look at the road, and if you look at the road, you'll feel it that you are not in Mississippi. It's recorded, right?
There is a stark difference between Jackson and other zones.
Okay, so what is the challenge there? Why it happens? Like the bumpiness, how the bumpiness is connected with the permeability of the sun.
Cleaning soil,
Okay, shrink cell is one thing, and then why we have the bumpy load? Adrika, why we have the bumpy load?
In some places it gets some water and some places not.
fast water.
When it rains, does it rain at a certain spot and the other spot remains dry?
In every place water won't take the same.
Here permeability,
When pressure is applied over the pavement, the water doesn't compress as much as the soil. So when it travels to one place to other, the place where it has water, it doesn't don't compress so much than the place that doesn't have water. Something like that.
But why the wavy pattern? Any idea?
something to do with the geology.
How many of you are familiar with the wavy pattern of the expansive soil pavement? Any idea?
In case of rain, the soil absorbs a lot of moisture,
Okay, very good. Then,
and as it is the soil is clay, it gets soft.
sure. But it gets softer all over the place. Why it creates the wavy pattern? What is the mechanism of having the wavy pattern?
Surface tension.
The desiccation,
What?
desiccation.
The
When the cracks-
desiccation definitely has some influence on it, no doubt.
So because when we have the cracks, the water will accumulate in some spots, so it will make weaker soils.
Good, you're right. Basically, what happens, let me try to draw from her. Okay. So what happens there is, this is our roadway. And then under the roadway, we have like, this is the pavement, this is our surface base, right? And then underneath, we have the substrate. So let's say this is our substrate. This area is substrate. And in Mississippi, the rule is, I think, in most of the cases, aimed at to an undercut. So wherever you have the pavement, you cut it, excavate the top 3 feet, replace the top, bring new materials, and then build the road. Filling. But it doesn't have any influence on your subgrade. Sorry, on the waviness. That may cut down some part of it, but it's not the complete solve. And then there is another problem there. The problem is, let's say this is your pavement, you do a cut, undercut, right? You replace the soil. And then you build a new materials in. But then what's gonna happen? You have the water, right? Water comes in,
Infiltrates upgrade.
and then over the period of time, it will create a wet area. Right? Basically, you're creating a bathtub here. Because underneath, again, your permeability. Underneath, your permeability is very, very low. Right? So underneath your permeability is very, very low in soil.
There is clay.
And water cannot pass through.
So there will be like some kind of punching, right? Now the materials will punch through the clay because now your water is sitting here. So this area will be very, very wet. Clay with very, very wet water in it. So what is the bearing capacity of those areas?
Really low. Very low.
Very low, right? So it will have some,
Corrugation, sorry.
it will have some punching in, right? So whenever there is a punching, what happens?
It's down.
You punch, what happens?
Some places go up and some.
Go up and some places go down, right? So if your volume has to be adjusted. Now you're pushing it here. It's punched through this. So it will come out somewhere else. Right?
But will it be uniform?
When you have like thousands of vehicle pass on top of it, it will readjust it, right? Think about the loading, continuous loading on top of it. That's one way. That's one way. That is one influencing factor. There is other influencing factor. You have the water entrapped in, right? So whenever a vehicle is passing through it, it's great one.
Widening.
This is perturbation.
And that excess perturbation is pushing the soil, right? Internally. Both directions. So if that water is pushing the soil in both directions, it will also try to have some lateral movement. It's a very good research problem to work on and find out how you have the wavy pattern development. You know,
Quantifying that matter. How much-
quantifying the mechanism of developing the wavy pattern. What influence or what are the criteria that influence the development of the wavy pattern? If you can find it out, that will be a terrific findings and solve many problems. And then there are other things too. So now what happens is like you have a bathtub condition, but at the same time you have the permittivity or transmissibility of the moisture coming from the sun, right? So during the dry period, this area will get dry. But the middle area is always going to be wet, right? That also depends on your permeability of the soil. How much moisture is going to hold, right? Anyway, so it's a very good topic to work on. So many people are trying to solve the problem, not yet being solved. You know, the only way people try to do it, not only ways, like several ways. One is you cut, you replace it with a good materials, good fill materials, and then build it on top of it. That's one way. The second way is you have the existing soil, you try to change the characteristics of the soil by adding some lime in. Now, what does the lime do?
Expand.
Absorb water.
When expand.
No, lime try to do some chemical reaction.
Produce it.
Not produce it, lime try to destabilize the activity of the clay. These clays are very active because they extremely high affinity of water, right? Because of their kaolinite, montmorillonite, and what? Elite, kaolinite, and montmorillonite, right? So which one is the smallest one, and which one is the largest one?
Montmorillonite is the smallest,
And
elite is the largest.
elite is the largest. So do you know the surface area of the elite and montmorillonite?
I don't know exactly the number, but the Montmorillonite has a huge surface area comparing to the others.
Okay, I think we have it here. That's
Yeah,
what
you talked about it last class.
it should be here. All right, clay mineral, right? Yes, right here. So these are the surface area of the kaolinite, elite, and montmorillonite. The kaolinite is 15, montmorillonite elite is 80, and montmorillonite is 800. You know, so you're gonna cut down the high charge surface area of the montmorillonite. To destabilize it, people try to use the lime, and lime do some chemical reaction and create some bond with it. That cut down some expansiveness. But the problem is, you know, how you're gonna do the milling and mixing with this soil. So all the laboratory experiment of the stabilization of the expansive soil with the lime is great. It's really great. Why? Because how you create your samples at the lab
You see, it's created in ideal condition.
is in the ideal conditions. You have the sample, you break it down, you make it like powder, and then you add the lime. You know, there's another powder, and then you mix it together. Then you add water in it. You make like a dough, and then you compact it inside your sample, inside your mold. So all the results are great, right? What happens in the field?
It's not representative.
At all, right? In the field, what happens? You have big lump, right? You just do the milling, and you throw the lime on top of it. You have like certain parts, right? So when you have the certain parts, if it mixes well, it's fine. If it is not, it's not. So let's say you just started mixing it, and then there is a rainfall. Then what are you gonna do? It changes the moisture content, right? Now the clay already has the moisture in it, so it's not dry. You try to break it. Will it be broken? It says those are like big lump of clay, and that will mix some part of the lime, but will it be like uniformly distributed mixture?
No.
There is absolutely no way. So you'll have the localized vulnerable spots. So that also didn't work. It's there for a very long time. Very long time. People are using this. So basically, to fight this clay, all we tried or we did is only these two techniques. No other techniques are popular at all. You can try. That's not popular. No one has a trick. It really doesn't matter. Because The first thing is you can do something, you can find out something, you can have like a terrific research outcome. But if it doesn't have been adopted in the industry, that technology has zero value. That's how it is. Especially in the civil engineering. If you cannot do the technology transfer of any technology, even if it's your learning, it has absolutely zero. We can have a clap and we can be like very happy publishing a paper. But how many papers is being published?
So many papers.
So many papers, right? So how many papers get noticed?
Those which have practical application.
Lots of paper gets noticed.
Most of the papers get unnoticed. Only few papers get noticed, unfortunately. You know, that's how it works. So the best idea is you have to sell your research. So whatever the things you do, you have to sell it. So how we can solve this problem? What are the factors that is influencing the problem?
Particle size.
First of all, the clay. Can you change the clay? No. Can you replace the clay? And who is the one of the major contributor in it? And temperature. Climate change is a secondary influence body, not the primary. Climate change is going to change its behavior, so it will readjust how it behaves, right? You're changing the climate means you're changing the rainfall, you're changing the temperature, is going to readjust the behavior of the expanses, right? Out of all the natural disasters or the loss from the hazard, expansive soil is the number 3 out of all loss. Expansive soil is number 3. You know, I think the number 1 is earthquake. Now, why earthquake is so bad, and what's the challenges with earthquake?
You cannot predict it accurately.
And
Instantaneous damage. Right.
That's the side. Loss of livelihood is really high in earthquake.
failure is catastrophic, right? Have you seen the news yesterday?
Morocco.
There are 2 major news for the geotechnical. There are 2 major damage, major failure. One in Morocco, the other one in Libya. How many of you know about Libya?
I do.
You do? Can you explain?
So they had a hurricane over there
Okay.
and some flooding. They had 2 dam failures, I think. Yeah.
They have 2 dam failures, right?
Yeah, they have so far like more than 2,000 dead people and like 2 cities were wiped.
The hurricane created catastrophic flooding. That flood washed out the dam and it opens all the reservoir, right? And once you have a breach, you cannot do anything, right?
You cannot fight the water.
You cannot fight the water. The only one person who knows this better is him. You can fight the water. That's for sure. What is the best way to fight the water?
Let it
Flow.
let it flow. have it to have it flow in a controlled way. You cannot stop it, but you can guide it to a safer way, but you need some precaution for it. It cannot be done instantaneously.
So the bottom line is you have to be proactive, cannot be reactive,
Yeah.
right?
Yeah.
There is no way you can hold the water in a reactive way. The only way is the proactive way, right? Why?
Just stay away from the water.
Because it's a catastrophic failure. Most of the catastrophic thing comes with so much energy in it, right? So whenever the energy is there, the amount of energy is there, if you wanna prevent it, you really need so much energy to hold it back, right? So it comes with so much energy. But if you become a proactive, then what you can do? Again, I'm becoming philosophical.
Just do more inspections, maintenance. Try to, I don't know,
You can minimize the,
take precautions.
if you're proactive, you can minimize the damage.
Yeah, we can minimize the unleash of the energy, right?
You can control it.
We can control it. So we can keep it like dormant. As far as we can keep it dormant, it's good. Okay, anyway. Over there?
Yes, just came back.
Okay, good. So we can start, right? It's a new lecture notes from it's the chapter 5 of the advanced soil mechanics of Geo-DART book. So basically, we're going to talk about the seepage, and we're going to also talk about the cloning. Okay. So my major objective here today is to cover the cloning. So let's start the discussion. So today is our lecture number 4, right? 4. Okay. So that's pretty good. So and I'll try to cover it like in 35, 40 minutes class. So we already know that the Q equal to KIA, we discussed before, right? Q equal to KIA, you know. So we can use that formula, and ultimately this is the Laplace equation, which is a differential equation to solve the problem, right? It becomes the changes in the height and with the different permeability. Basically, the two-dimensional equation or the three-dimensional equation looks like this. It says kx, ky, kz. So far, we are talking about only k, right? Not kx, not ky, not anything. But now we have the kx, ky, and kz.
Isotropic condition.
Isotropic condition or anisotropic condition. So what is the isotropic condition?
Isotropic kx equal to ky equal to kz. And anisotropic, all will be unequal.
Unequal. So we have like different influence in the different areas, right? That is coming up with the anisotropy of the flow. So is there any type of soil where we might have anisotropy or might have a high chance of building up the anisotropy? In any material?
Different kind of strata.
Give me a example of a earth material which is homogeneous and isotropic. Truly homogeneous and isotropic.
Which
Sea beach. Okay. So what do we have in the sea beach?
sand,
Clean sand.
clean sand.
Clean sand, right? So clean sand has distribution of the pole. So that pore space is distributed all over the place equally, right? So that's the isotropic condition, perfectly isotropic condition. Now within the sand, if you have like some mixture of the fine or like some fine is there, you have some fine content in it. Now what's gonna happen? That fine content
will reduce the permeability.
will reduce the permeability and then it's trying to be entrapped within the void, right? So how does the water will flowing through that? It all depends on that. And how about clay? You have the clay, you have some mushroom. But if you think about like how any construction is being done, you know, let's say we have the embankment field, looks like this. Any embankment field looks like this. So if you have an embankment field looks like this, how the construction will be done? First we make this, we make this, we make this, we make this like this. Then maybe we make this, we make this. Is that it? Or more general, we do it like layer by layer, right? Isn't it? Any embankment. So if we feel something, we are dumping some soil, having the roller pass on top of it, and then build it, right? Dumping more and dumping more and dumping more, compacting. That's how we build it. The question is the way we are dumping the material in between layer 1 to layer 2, layer 3, layer 4, layer 5, layer 6. In between each layer, what is there in between?
Interface.
There is interface, right? So what does the interface do?
It interlocks error, frictional roughness.
So what happens between the interface?
Sliding or
Why? No,
sliding. Yeah. Sure.
it's a weak spot, right? It's a joint. Interface is always a joint, right? Two materials, they behave like a sheet, right? Interface behaves like a sheet, like a book. You have different pages. So each of the pages has like something, right? Isn't it? So when you have the clay constructed on top of layer by layer, so each of the layer behaves like a sheet, right? In between the sheet, what happens?
Particle difference of K.
In between the sheet, each of the sheet will behave like conduit, right? Water can flow through. At least those are the weak spots, right? So water can flow through those sheets very, very easily. So through that, your permeability may go up, right? Along that you know. So what basically happens is your KH usually goes up than KB. You know, it's a very typical problem. Your KH goes up than KB. You get my point? Is there any situation where your KB may go up than KH? Come on. Any idea where KB may go up than KH?
When we have, I would say rock piles,
When you have
rock piles, it will have higher
Rock.
KV, and then the soil around it.
other than the rock piles, is there any other phenomena? Any other phenomena is like the material behavior or something that may create your KB is higher than KH. So you have an anisotropy, but this anisotropy gets flipped. So in the clay, usually there is the anisotropy. or fine grained material, there is the anisotropy because this is how it's being constructed, layer by layer, right?
When there is desiccation,
Very good, when there is a desiccation. In the expansive soil, your Kb is higher than Kh.
Correct.
That's a major theoretical difference on expansive soil. That's a completely different view in the mechanistic principle, you know. So the anisotropy for the expansive soil is different in the upper layer, in the active zone. Below the active zone, again, is you have the horizontal anisotropy. You get my point? Okay, very good. So now how to solve this problem?
It is a differential equation.
It's a differential equation. So how we can solve
We need boundary condition,
it?
initial condition,
And
as an assumption.
so what is the best way of solving the differential equation? Do you know a method that can solve a differential equation?
ODPD is a PD. Partial and
Laplace.
Laplace. Fourier transform. Fourier transform.
Fourier transform. And
It is Laplace here.
so every time you need to do that. What is the difference between the engineers and the mathematician?
We engineers assume. We engineers assume easily,
Or a spike.
but we don't like, we just assume it in a simpler form.
Therefore, that's right.
What do we do?
Simplify.
We simplify the problem, right? This is not good, we don't like it, so we simplify. Right? If you go and talk to a mathematician that you want to solve it, they'll take the pen and paper and they'll try to solve it in a different way, right? So over the years, engineers develop different methods to solve this.
Numerical method, numerical Range-Kata method.
Numerical methods, right? So one of the very popular numerical method is the pancake.
Finite element, yes. Finite element, finite difference, finite volume. The three kind of mathematical methods to solve
Any differential.
any differential.
So all the differential equations is being solved using the finite element. That's why all the seepage analysis software are finite element. It's not a limiting. All seepage analysis software are finite. Because other than finite element, you cannot solve it. Or you have to go for the derive and use the Mathematica or other.
There is one called Range-Kata method. I remember from our undergrad. It was really difficult question, 3 or 4 page.
Careful pay, right? And that's not efficient, right? You need to make money. So if you're solving the problem, no one they're going to pay you so much money. It's a competitive world, right? So you have to come up with something. You need to develop some chart method or something so that you can survive and win big. So
You don't have some method, another method.
yeah, those are numerical you're talking about. So, but the FEM is the most popular one because FEM is scalable. The basic reason FEM becomes popular because FEM is highly scalable. You know, anything is scalable, make a big business. If you cannot scale it up, you cannot make a business out of it. So in terms of the methods, FEM becomes really popular, even though it's pretty complex. But you can create a software with it very, very easily. And then you can just go with the iterative process, and that iterative process will give you the solution.
We need to build that GUI.
Yeah.
Then the interface. for
Yeah, the GUI is very popular. Like in 1990s, GUI is like, if someone builds a GUI, they make a fortune. In 2020, if you're talking about the creating a GUI, that's the requirement. If you're not creating a GUI, no one even think about using your software. That's how it works, right? Anyway, so the question is how to solve that problem. And to solve that problem, there are many methods. But one of the most popular methods to solve it is creating this. It's known as the flow net. Yeah. So what happens in the flow net?
There are some
And
potential-
before we go to the flow net, let's also discuss about the seepage flow. We can also discuss about the seepage. So what happens in the seepage? We discussed it before, but let's rediscuss a little bit. I think it's better here to discuss again. So what happens during the seepage?
water flow to the pore space.
Water flows through the pore space of the soil,
in the-
right? And that creates what?
Piping it.
That creates the piping action, okay? So with that piping action, what is the piping action?
Internal
It is into the pipe flow.
What?
erosion.
Internal erosion. First, we are trying to understand what happens while the water is flowing through the soil. Let's try to draw a pipe, okay?
Well, when you have high hydrostatic pressure, and then the water starts to go through the pores of the soil.
Let's try to understand it here. So let's say we have a pipe, and in between the pipe, we have compacted soil in it, okay? And now we're trying to put some, let's say, some water hose here. And within the water hose, we are trying to push water in. Now, what's going to happen? This water will try to flow through this, right?
Pressure flow.
It's trying to flow through this. Right? Yeah, it's horizontally. Like it's flowing through it, right? So when the water is flowing through the pipe, what will happen?
Create line. It will create pressure.
Water will
Surface
flow
of the
through it.
pipe.
Water will flow.
Laminar flow.
Okay, and
There will be, water will be streamlined.
okay, at one point. So let's say water is getting in at a certain pressure, let's say 50 psi. Okay. Here. Give me a number when the water is coming out from here.
Like friction loss, some head loss.
It's going to lose that many power, right? So whatever the pressure is getting in is not the same pressure coming out,
Head loss.
right? So there will be like some difference. Okay, let's have 5 psi. So let's say we have a 5 psi.
45 psi head loss.
So in this one, we are going to have some kind of head loss, right? So how about I go back and decided to increase the length of the pipe and increase the amount, the the soil in the pipe. So let's say we increase this length,
More head loss,
more head loss, right?
because L is
So it's going to, let's say if we keep increasing the length, then what will happen after a certain time?
Water will not flow.
Water will not flow. Water will go up to a certain point and then it stop, right? Why?
potential drop.
Due to resistance.
Bernoulli
Due to the
equation.
resistance. So all the resistance that the soil is going to give back to the water is going to nullify all the pressure coming from the water flow, right? So whatever the energy is coming through the water pressure is being dissipated within the soil, right? You get my point? Now let's say now you try to increase, like let's say you have a clogged drain and you want to clean it, flush it. Then what are you gonna do? First you push some water, nothing's coming out. Then you try to increase what?
Pressure.
The pressure, the force, right? If you increase the pressure, then what's gonna happen?
Jet flow.
One of two things can happen. Either the clog might get released or the pipe may burst. Whichever is lower.
Whichever stress is lower, right?
Cooking stress.
But before that, you will see nothing, right? You're putting the energy, nothing is happening, right? But in this case, like from the 50 psi, so let's say, let me try to draw it again. Let's say I'm putting a 50 psi, all has some soil in it, okay? All has some soil in it, and then we have the water. So let's say when you put the 50 psi, water just comes up to here, okay? When you put the 50 psi. Now, if we increase the water pressure to 100 psi, or let's say 80 psi, what we can expect going to happen in this one?
Some soil will come out.
It's going to compress the soil.
First of all, what's going to happen is more area will be saturated, right? That's the first thing. Then, if the water will come out or not, or like there will be piping or not, to have a piping, you need to create a flow. If you don't have a flow line, there is no pipe because it's going to stop there, right? Nothing is coming out. So water just get inside and get stuck, right?
Yeah.
So what is seepage? Seepage is this action where the water is flowing through the soil and the soil is resisting the flow of water. You know,
And the water is moving through slow soil particle under pressure.
under pressure. There has to be a high pressure condition. If there is not a high pressure condition, there is no seepage. You know. So let's say now let's try to break it down. So let's say what is happening. Let's try to find out if there is any flow here. You know, if we wanted to find out if there is a flow here, then how we can calculate that flow.
If there is a flow here,
How we can calculate any flow?
E equal to VA. E equal to VA.
Or Q equal to KI, right? Very simple. It's the basic formula. Q equal to KI.
A is constant, K is constant. So only I induces the flow.
Only I is the flow, right? So what is that?
Hydraulic head or gradient. Hydraulic
Hydraulic.
gradient. Del H by del H.
So what is the hydraulic gradient? What is hydraulic gradient here?
Here,
In the pipe flow, let's say what is the hydraulic gradient here?
0. Sorry,
within a unit length. What is the Hadley gradient here?
del H by del H.
Water is flowing through it, right? So let's say at this point here, your water pressure is 40 psi, and then after a certain point, it becomes 35 psi because it's dropping, right? So you know this to drop, and if you can find out the length of it, can you calculate the I?
Yes. Pipe by L. Pipe by L.
Pressure difference by the.
Pressure difference by horizontal distance.
Pressure difference by divided by the length, right? Now let's say you wanted to convert it into a unit. So whatever the pressure difference is there, let's say you are trying to break it down in every 5 psi drop, you consider one length, one unit length. Then you can come up with like a resistance, right? Unit resistance for a certain drop. Isn't it like that? Right?
Can you please explain one more?
So is it like I'm just throwing arbitrary number here, like 40 and 35, right? So if we know the 40 and 35, maybe our length is L, right? Let's say that length is 10. Okay. Now if you consider between 40 and 25, you know, that length may be 17. Okay. So we have no idea, like what part is influencing what. So let's say we are trying to go back and try to make it like uniform distance. Then what we can do? If it's going to be a uniform distance, then it will have, if it has a uniform distance, then that uniform distance will have
This resistance.
a certain resistance
Certain drop.
or certain drop, right? So if we now try to break it down, so let's say this is not a pipe, but if we have a series of pipe, and in between each of the pipe, we idealize the situation, then what we get? Let's try to find out here, okay? So let's say we have a water and we have a sheet pan, okay? So this is the sheet pan. We have the water, and right here is our ground line. This is the ground line, okay? Now, whenever we are having the water on top, what will happen? Water will try to flow through the sheet pipe, right? Like this, all the way and come out. So it has to travel all the way, right?
Streamline.
Outer water has to go all the way and come out. Like this, right? So in this case, how we can calculate what is the flow? There is no way we can do it, right?
We need to construct.
But the engineers are smart, right? We don't think like a mathematician. We try to solve the problem in a very simplest way. So what is the simplest way we can solve?
We consider a unit area and calculate how much water is flowing through that area, and that is the flow. I think like flux or light,
Like, yes.
flux or flux.
Okay, that's very complex. It's still very complex. How we can make it even simpler?
We make it by ourselves, then we calculate it.
So how about this? So we already know the pipe phenomena, right? That's very simple. What we consider, if we know like one pipe flow,
And then multiply it, how many pipes are there?
right? So can we create a pipe?
Yes. Like,
So let's say the water will come like this, like a pipe. So this is our one pipe, right? let's say we take another pipe. This is our second pipe, right? We are just breaking it down, making the problem simpler, nothing else.
And then considering potential drop to some points.
And then another pipe. So just breaking it, making the problem smaller. It is a big problem. Now we are trying to break it down into smaller problem, right? So let's just consider it because of pipe flow. So all the pipe, water is flowing through each of the pipes. And then inside the pipes, what is going to happen?
Head loss.
It loss, right? So let's say this is our pipe, right? In this pipe, what will happen?
Head loss.
Head loss. So let's say in this pipe, there will be some kind of head loss, right? So in this one, if we know the length of the pipe, right? Here we need to calculate what? I, right?
Yes.
To calculate I, we need to know the head loss and we need to know the length,
Yes.
isn't it? That's it. If we know the head loss and we know the length,
Divided by each other, then we will get I.
we'll get I. And for A, how we can make it simpler?
Unitary.
Unitary unit length. Problem solved. Right? We are doing it today. So everything is divided by 1.
Z
Or per square,
Z equal to 1, let's assume.
let's assume, right? We are good in assuming. So our starting point is assuming something and then start the problem. So simplify. Isn't it? So now how we can make it simpler? First we'll break it down into pipes. Make it simple.
Made
Right.
1, 2, 3 pipes here.
Okay, make 3 pipes. And each of the pipes there will be some drops. So if we make it like it will have a uniform number of pipes and each of the pipe will have the same number of drops, the problem solved. We can go to sleep. Isn't it? Right?
1, 2, 3, 4, 5, 6. For 3 pipes, each pipe will have 6 drops.
Whatever the drops, we will make it. You know? So how we can make it the most simplest way? What is the simplest way of making something in terms of assuming? Square,
And perpendicular.
right? If we make it square, even the problem becomes simpler. So how we are solving a differential equation?
Breaking it small.
Assumption, boundary condition, initial condition.
Just making it in now few number of pipes, and then each of the pipes has like only few other assumptions, right? Is it truly accurate?
Approximate solution. Approximate solution. It will
But
be.
is it workable?
Yes.
Yes, right? Isn't it? No doubt. So what we should do now?
Make that area square
Make the radius square.
and the line those angle to be 90 degree.
This is going to be 90 degree, right? So let's come up with some rules. The rules is, let's go back here again. We wanted to solve it right here. Okay. So in this one, what we can do, we have the pipe flow, right? Within the pipe flow, we don't know how many ways the pipe is going and how big the pipe is. But if we just make it down, taking the idea from finite, all you have to do is you have to make it small pieces. But all the pieces are equal. So if you solve one piece, you just scale it up to all other pieces, right? So let's say we just break it down to an equal number of pipes, and within each pipes we have the equal number of squares, right? Then in this one, this is our head difference and this is the length. Sorry. In between these two, whatever that this number two are our head difference, and then we know the length, we should be able to find the I. If we get this I and make sure this is square, means this is scalable, right? It's equal everywhere. We are just trying to take a sample, but that sample is representative sample. So how we can make it a representative sample? If we have the conditions in a way that sample is equal in everywhere, distributed all over the place, right?
Yeah.
Then it should work. That's what is being done here. You have the flow, you know that how the flow is going. All you are doing is making some assumptions. So what is the first assumption?
Flow should be perpendicular to the cross sections.
The flow should be perpendicular to the cross section. Okay, so let me try to make it clean. Very clear. Now, let's take that assumption again. So, first of all, this is our control structure, right? Or sheet panels. What is our number one assumption? First thing is, we need to find out our inside and outside condition, boundary condition, right? So, our number one condition is, this is our flow line. This is the inside flow line, the first. And what is the last flow line?
To the impermeable layer.
This is our flow line, all of it are flowing, right? So this is a pipe that we may have the inner boundary and the outer boundary, right? So we just find out these two boundaries. And in between the boundary, what also happens? So basically, if we try to make it like idealize it, this is our first boundary in the pipe, right? And this is our last boundary. So our last boundary is this one. Our first boundary is this one. Okay. So basically, the problem that we are trying to make looks like this. Which one is like this? You know. Then what is our second assumption? In between our pipes, we have parallel flow lines. Now, in this world, this is the idealized world, you know. But we are not in an idealized world, right? Our world is different, like this. But we want to keep the same assumptions. So we want it to be a semi-perfect parallel lines that follows from our starting line to the end line, right? So we are trying to create singular line that is going to end like this, right? What is our third assumption? In between the flow lines, we should have our drops, potential drop lines, right? Or the pressure drop lines. And how these lines are internally connected?
90 degree.
90 degree between the flow lines.
Flow line and potential line.
Wait, yeah, the potential line, let us use a different color. So this we cut at 90 degree with each flow lines, right? So let's cut each flow lines 90 degree. Okay, cut at 90 degree. Got it? So now if we come here, we get our outer lines. So our flow lines will be parallel, right? These are parallel lines. Correct? And then our potential lines are going to be perpendicular are cutting at 90 degrees each line. Isn't it? If we have that, then all we have to do is what? We need to find out the I.
For one,
Right? So how we can have the I?
the same unit system way. Total head difference here is 2.5, 3 minus 0.5.
Okay,
The here water level is the 3, here 0.5.
okay.
The head difference that will increase the flow is 2.5.
So if we have an equal drop, what you're trying to find out is del H over L, right? The equal drop. So what is our drop?
2. How many potential drop we are considering here? So
It depends. Okay, so what is our first drop? How many drops here?
1, 2, 3, 4, 5, 6. 6 drop.
6 drops.
6 drop equal to 2.5. So per drop will be 2.5 divided by 6.
The number of drop, right? So our del H is what? Del H is
2.5.
whatever the height, like our potential height or the potential energy divided by the number of drop, right? Correct? So that is a del H. And what is the L?
There is that length. The flow length. L.
L, right? L is the flow length. Okay, so we are coming in the flow length. So valid for only one flow. But we wanted to get to the whole area, right? So we have like one pipe, one area. So if you want to calculate the total flow, then what do we have to do?
Just multiply it.
With the number of pipes, right? So we just calculate it for one pipes, and then we break it down in 3 or 4 or 5 pipes. So all you have to do is whatever the number we are going to get, we just need to multiply it with the number of pipes. So what is our pipes here?
Total 1 by
What are our pipes? So this is our first pipe, right? Which is our flow lines. So this is to calculate the flow lines. The idea is you have to calculate the pipes. So this is one pipe, right? One flow line, second flow line, third flow line, fourth flow line. So you have 4 flow lines. Those are your pipes, number of pipes. Got it?
Yes.
So all you have to do is we need to calculate,
for 1 and then multiply by 4.
then multiply with the number of the flow lines. So basically, in the flow net problem, the equation is, where is the equation?
That is the equation. E equal to H NF by ND.
That's your equation, right? So in this equation, what we have E equal to K, which is known, right? And then H over ND is what?
Number of flow lines H by ND.
H by ND is what?
For 1. For 1 pipe.
For one pipe, right?
Multiply by total pipe NF.
By number of total pipe NF. Number of flow lines. That's your flow line. Okay. So let's try to do a problem here. For the flow net in figure 5.27. So what is figure 5.27? The one we just looked at, right? No, this is 26. Okay, so this is the figure 5.27.
That's a dam.
That's a dam. That's a concrete dam. This is a concrete dam. Okay.
There are 5 pipes.
This is the flow net. So the first thing we need to understand is how to create a flow net. I'll explain it again. I'm just showing you the problem, but I'll explain it again in the next slide because this is one of the most important criteria for the earth dam, how to create the flow net, So it's really important. So there are like 4 criteria for creating the flow net. The first one is you need to identify the equipotential lines and equipotential drops, right? And your outer is the these 2 lines. So this is your outer line. This is the first flow lines, right? And this is the last flow lines. And in between those flow lines, your every equipotential lines. We intersect the flow lines in a perpendicular manner. And every flow line and the equipotential line will create a rectangle. Right?
For dam.
For anything. That's the basic of the flow net. So let's say your starting point. So you have to do it in many trials, not one trial. You have to do many trials, So this is the finished one, but when you start doing it, you never get it to the finished one, So basically what happens here is like your flow lines are parallel, right? So if I draw it like this. If you draw it, you may draw it in a different way. If your flow line is same as Fine's flow line,
Copying.
copy it. Because there is no way your 2 flow lines can be the same. It's very unlikely, Then what is the second idea? Your equipotential drops should cut the flow line in right angle. Right? So what is your starting point? Here. It goes like this and coming here, coming here, coming here, perpendicular, all perpendicular, equal. If you consider it equal like this, So I get it. Now we just have to calculate what is our top water table, which is H equal to 10, and right here is 0. So the difference is 10. The difference is 10. Always look at the difference. So it can be like elevation 100 and right here elevation 90, like this. The best idea is look at the elevation. Don't look at the height. And then you calculate the height by eliminating the by the difference. That's the best way of doing this calculation. Now what? Now what is happening here is Q equal to AI. So this is between each lines. This is your H1, H2, the drops, right? Equal drops. So this is your del H, which is coming from the flow net. And what is the L? This is the L by B. This idea, this calculation is also very important. That's what I'm discussing, because later on you also need to consider it. When you consider your rectangle, your L and B is eliminating each other. But if it is not a rectangle, sorry, not a square, but a rectangle, then you have to consider it. So basically what's gonna happen is if you have it in a different way, then you have to calculate the L to get the I, and then this is your A, right? So what is the A? You know the B, and then the other perpendicular to this side is 1. Correct? So you get the area. So this is A. All right? But this becomes equal, so you can get to the ND and you finally get H over ND. So if we take that numbers, first of all, what is the height the water rises the piezometer slit at A, B, C? And if K equal to this, then what is the seepage loss? Yeah. So the first one is all you have to do, we need to calculate the number of flow lines and number of drops. So how many flow lines is here?
1, 2, 5, 4, 2, 3, 4, 5.
Flow lines. Flow lines is 1. To calculate the flow lines, the idea is we need to calculate the pipes.
5 plus 1.
No. Just the pipes, not plus 1. That's why I started with the pipes. You know, you need to calculate the pipes because this is your flow path. Flow lines are not the pipes. You know, you have one pipe, you have 2 pipes, 3, 4. In my flow net, there are 5. In their flow net, I think it's 4. I think I had one more. No,
Same. They also
same. Okay, so 1, 2, 3, 4, 5. So 5 flow lines. Okay, NA equal to 5. And how many drops? ND.
1, 2, 3, 4.
ND is 1, 2, 3, 4, 12, 5, 6,
12.
okay, wait. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So this is 12. So ND equal to 12, right? And then let's say there is a point B, there is a point, where is point A? Let us say point A. Here is a point A, and where is point C? C is here? Okay. So any point along the flow line, sorry, the equipotential line has the same pressure drop, right? Has the same pressure drop. So it means at point A and point C should have the same pressure drop. And what is the number of pressure drop? So this is 10. So right here is 10. This one is what? At this line, what is the pressure?
It is equipotential, same.
Okay, so the first drop. So for each line, what is the drop? 10 divided by 12, right? At each line, this is your drop. Equal drop, equipotential drop. So what is the drop? 10 divided by 12 is what?
0.8.
5 by 6.
0.8.
0.8. So your drop is 0.8. Okay. Just makes our life easy. So how many drops we have? 1, 2, 3. So how many drops we have so far? 3 multiplied by 0.8 is gonna be
2.4.
2.4. So what will be the pressure along this line? Ten minus 2.4, right? So that's gonna be 10 minus 2.4 equal to 7.6, right? Meter.
But 10 minus 2.4 is which quantity?
This line. Before this line, you have this drop, this drop, this drop, 3 drops, right? What is point B? B is having 2 more. right? 5 drops.
So 10 minus 5 into 0.8.
5 into 0.8 is 5 into 0.8 is 4.
6.
So it's 6. So at point B, it's gonna be 6. Right?
At B, the head is 6.
Yes. At B, the head
Equilibrium
is 6.
potential is 6.
6. The pressure is 6. Got it? That's it. I don't know. My number might be different from the book. But it depends on your flow rate. My flow rate, I'm looking at it in a different way. You know, every flow rate is different. Number is going to be close. But not going to be very close.
So if I make more flow rate, will the thing will be accurate?
You can, but it's first of all, you need to understand why you created the flow rate.
Solve the math.
And
Make it smaller.
to make our life easy,
Get thing done.
right? So if you wanted to make it more accurate, then you're missing the perspective. Isn't it? Anyway, okay. So, bad example. What is the next question? If K is given 0.1 meter per second, then what is the loss? In meter cube per day meter. So this is in second, you need to find the day meter. So you have to do some unit transfer. I'm not going there. This is like, so to find it out, all you have to do is what? Oh, this number is not 0.8, it's 0.833. We have the same numbers. Okay, but we simplified it. Anyway, so our Q equal to K 0.1, right? Into H. What is H? 10 multiplied by ND. NF over ND. Number of flow lines. How many flow lines? 4, right? 4 or 5? 5. Okay, 5 over number of drops, 12. This is gonna be in millimeter. This is in, the unit is in millimeter.
Per meter.
Millimeter. So this millimeter we can convert it into meter. So divided by 1000, right? So we get 1 meter, and then H is in meter. So this becomes meter square, right? And NF over ND. So how it's, and then the unit length is in 1 meter, right? So that's 1 meter too. So in our B, so this is 1 meter. So this becomes meter cube, and then the time, so this is per second. So per second, we need to convert it into per day. So to convert it per day, what we have to do? Multiplied by second is 1 by second. So this number goes up, right? So everything goes up. So this will be so this will be 60 seconds. So it's minute. Sorry, yes, an hour into 24, right? That's the number. So I think that the number should be the same. Do they have it? Yes. This multiplied, so we get the number. So that's the number we're looking at. Oh, sorry, is in meter cube per day. So they're sorry, they converted it the K into meter per day. That's the number, right? 3.6 meter cube per day. Okay. So this is gonna be 3.6 meter cube per day meter. Do you think it's a big number?
Yes.
Can you convert it into gallon? 1 meter cube.
Around 1 gallon. Around 1 gallon.
1 meter cube.
If 264 US gallon, 1 meter cube equal to 264
It's,
US gallon.
about 951.019 gallon.
951,
951.01.
951. So less than 950. Okay, so it's 950 gallon per meter cube, right? Per meter. So multiplied by 3.6. So 950 multiplied by 3.6.
It's multiplied.
Oh, so it's 950. Okay, now 950 gallon per meter, per meter,
Per meter.
per unit meter, right? So let's say you have 5 kilometer long. The spillway is how big?
So it is.
3 mile or something, so close to 5 kilometer, you know?
Around 3 miles.
3 mile. Okay, so if it is 3 mile, so let's say 3 mile is 5 kilometer. So this 5,000 meter. So 950 multiplied by 5,000
It is 47 lakh 50,000
gallon
gallon.
water you are losing.
So high.
Right?
Structure is definitely going to fail.
So if you have that amount of water coming out, what will also come out with it?
Soil.
So
Soil, the amount of soil.
I
that
think-
comes with it. So that will kill it, right? So this is a very high number. Why? The K
Is real high.
real high. K is like sand. 0.01. 0.01 millimeter per second, right? So basically it's like 0.1 centimeter per second. It's a pure sand, right? Now if you can make it like 0.1 10 to the minus 9 or 1 10 to the minus 9 centimeter per second. So that number will go down
Significantly.
significantly, right? So all you have to do here is to change the K. That's the basic of any time.
Dr. Khan, does vetiver grass change K has the ability to change K?
Some, in some extent. Some extent. Theoretically, some extent. For sure. And test it. But theoretically, for sure. Why?
Because the root attracts the water.
So,
The root
Is the drainage part.
make the drainage path or cut the drainage path. Root should create an unsaturated zone. Right? Whenever we are in the unsaturated zone, permeability goes up or down.
permeability goes down.
Degree of saturation curve. Look at this. What happens? So if your degree of saturation goes down, means soil is getting drier. So if the soil is getting drier,
K is
it is increasing or decreasing?
decreasing.
It is decreasing, right? Unsaturated zone. So your permeability, so if your degree of saturation is, so soil is getting drier. Your permeability goes down. Why?
Things should not be inverse.
Why? Because it goes down because now you have the air in it. Air and soil interaction. So the air is there. The air will try to cut the water flow. Okay? It will cut the water flow.
Student here, encourage water flow. There is
No.
void in it.
If you have the air in the pore space, like think about you have a pipe flow, and in between the pipe there is a bubble, trapped bubble. Then what's gonna happen?
It's gonna,
Unless you can take out the trapped bubble, you never have the full flow in the pipe, right? So this is exactly going to happen when you have the trapped air. Okay? Okay, so I wanted to finish by 8:30. So it's 8:36, so I think we can do it. Thank you. Any question on the floor? So now can you solve the problem on the floor?
Is the concept is clear now?
Concept is clear now? Should be. All you have to do is make it like it. Okay. Thank you.
Thank you so much, Dr. Khan.
Thank you very much.